Hello and welcome. Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss catalytic effects, mostly known as equilibrium and kinetics. When I discuss a process problem, I'll frequently qualify my views by stating, let's assume equilibrium conditions have been reached. What I'm doing is choosing to ignore the effect of time on changes in composition. I'm ignoring the effects of kinetics on the process. I'll make such assumptions to simplify complex discussions. It's a bad habit, which sometimes gets me into trouble. Kinetics versus equilibrium. A reaction that is limited by equilibrium is finished. Waiting longer will make no difference. An example of this is the absorption of H2S from refinery fuel gas into an amine solution. Depending on the concentration of the H2S in the fuel gas, the amine solution will become saturated with H2S. Mixing the fuel gas and the amine solution for a longer period of time will not push more of the H2S into the amine solution. The reaction is complete, and we say the absorption of H2S by amine is limited by equilibrium. On the other hand, a reaction that is limited by kinetics is not finished. Waiting longer will help to complete the reaction. An example of this is the absorption of CO2 from refinery fuel gas into an amine solution. The CO2 will react with the amine to produce a stronger chemical bond than with the H2S and amine. CO2 reaction with amine goes slower than the H2S reaction with amine. Mixing the fuel gas and the amine solution for a longer period of time will push more of the CO2 into the amine solution. The reaction is incomplete, and we say the absorption of CO2 by amine is limited by kinetics or time. In the plant, then, we have two problems. H2S absorption is limited by equilibrium. CO2 absorption is limited by time. We deal with these two problems by: to extract the residual H2S from fuel gas, we circulate more amine solution. To extract the residual CO2 from fuel gas, we have more contacting trays in the absorption tower. A similar problem occurs in the amine solution regenerator or stripper as shown in picture. The H2S strips out easily. Residual CO2, which is more tightly bound to the amine molecule, requires lots of trays and lots of steam to strip out. Temperature versus time. If a reaction is too slow, there is a simple way to make the reaction go faster: higher temperature. Milk goes sour even in my 38 degrees Fahrenheit refrigerator after a few months. The milk will go sour much faster if I leave it on our kitchen table at 74 degrees Fahrenheit for a few days. Typically, for a non-biological reaction, the rate of reaction might very roughly double for every 30 degrees Fahrenheit increase in temperature. Regarding the example of CO2 absorption in amine solution, I said the CO2 absorption was limited by time or kinetics or reaction rate and not equilibrium. Perhaps I could increase the amount of CO2 absorption in the amine solution by increasing the absorber temperature shown in picture. Maybe yes, but maybe no. Maybe yes, because the reaction will go faster with higher temperature. But maybe no, because a higher temperature reduces the amount of CO2 that, at equilibrium, can be absorbed by the amine solution. Purpose of a catalyst. Increasing temperature to speed up a reaction is often a bad idea. If I have a plant that is desulfurizing diesel oil with hydrogen, so as to convert the sulfur in the diesel to H2S, I can achieve the required % of sulfur removal in two ways. Mix the hydrogen and diesel together and wait a very long time. Mix the hydrogen and diesel together at a very high temperature, 850 degrees Fahrenheit. At 850 degrees Fahrenheit, desulfurization will proceed quickly, but the diesel oil will also thermally crack to coke and gas and be useless as a fuel for trucks. What is wanted is a way to accelerate the conversion of the sulfur molecules attached to the diesel to H2S at a moderate temperature, about 700 degrees Fahrenheit. That's what a catalyst does. It does not change the equilibrium, it just makes the reaction go faster without having to increase the temperature. For a catalyst to be effective in accelerating the rate of reaction, it has to come into contact with the molecules of the stuff that's reacting. That's why catalysts have lots of surface area. Most of the surface area of a pellet of catalyst can only be seen with a microscope. As we try to desulfurize diesel oil, some small fraction of the hydrocarbon will turn to coke. The coke covers a tiny portion of the surface area of the catalyst. This slows down the rate of reaction between the hydrogen and sulfur molecules, converting to H2S in the diesel oil. The sulfur content of the diesel product goes above spec. To reduce the sulfur content of the diesel below spec, the operator raises the temperature of the reactor. This makes the reaction go faster, which is good. But it also increases the rate at which coke deposits on the surface of the catalyst, which is bad. The extra coke blinds off more catalyst area. The reaction rate drops. More sulfur is left in the diesel. The operator increases the reactor temperature to speed up the reaction, which leaves more coke on the catalyst. When this game is over, we are at the end of run condition. Many years ago, an engineer was hired by a refinery in Lithuania to redesign their hydrogen production plant, to increase plant capacity by 25%, and to reduce the CO2 content of the hydrogen product. The CO2 content of the hydrogen was 2%, and the new specification was 0.5% CO2 in hydrogen product. The process for CO2 absorption is the same as shown in picture. The only difference is that a potassium salt solution is used instead of the amine solution to absorb the CO2 from the hydrogen product. The potassium salt solution is called catacarb, as shown in picture. To accelerate the rate of absorption and deabsorption of CO2, a catalyst called LRS-10 is added to the catacarb. He had ordered a fresh supply of LRS-10 catalyst for startup. When he arrived in Lithuania, he was informed that the LRS-10 catalyst was stuck in customs and would be delivered any day now. He decided not to worry about the LRS-10 catalyst for two reasons. One, the plant operations chief informed him that there was already a catalyst in the catacarb solution that would be used for startup. It was a diethanolamine catalyst, not LRS-10, but still it was a catalyst. 2, you can't worry about everything. As lower temperatures favor the absorption of CO2 by the catacarb solution, he had expanded the capacity of the circulating catacarb solution aerial fin-fan cooler to cool the absorber tower and thus reduce CO2 in the H2 product. Another engineer stood next to him at the panel when they started the catacarb circulation pumps. He was totally confident. He forgot to mention that the operators in Lithuania didn't like him. Nothing personal. It was just that they didn't like Americans. So, when the cooled catacarb solution began to circulate, they were overjoyed. The CO2 content of the hydrogen product lined out at 3.5% CO2, well above the previous level of 2%, and far above his target of 0.5% CO2 in the hydrogen product. He was soaked with sweat in the chilly control room. The operations chief and panel room operators beamed with pleasure. Confused, he asked them to turn on the last fan on the aerial fin-fan solution cooler. The absorber temperature dropped by 10 degrees Fahrenheit and the CO2 in the hydrogen product went up from 3.5 to 4% CO2. Any further instructions, comrade? The unit chief happily inquired. He didn't answer. He couldn't breathe. For the next 3 weeks he engaged in a titanic battle with the hydrogen plant. 14 hours a day, 7 days a week. He raised the absorber pressure by 15 psi, which helped a bit. He lowered the deabsorber pressure by 3 psi, which helped a bit. He maximized the steam flow to the deabsorber reboiler, which helped a bit. He had open stripping steam piped up to the reboiler return nozzle, which helped a bit. He increased the circulation rate of the catacarb solution, which helped a bit. He shut off one of the 4 aerial cooler fans on the lean catacarb solution as shown in picture, which helped a lot. So, he shut off, one by one, over a period of days, all the aerial cooler fans. The absorber became quite hot, and the CO2 dropped to 0.5% in the H2 product. None of this made any sense. CO2 absorption in catacarb solution should be favored by lower, not higher, temperatures. Equilibrium conditions for CO2 absorption are always improved by cooling the circulating absorption liquid. The general director of the plant, an American, invited him to a dinner to celebrate the 0.5% CO2. Waiting for the main course, he thought about the problem. Why would raising the absorber temperature, clearly bad for equilibrium, reduce CO2 in hydrogen? Certainly, absorption efficiency is improving, not because of equilibrium, but because of kinetics. It must be reaction rate or time limited. Otherwise, the higher temperatures in the absorber would never help. Mr. American, he asked, what about the LRS-10 catalyst? Has it cleared customs in Klaipėda yet, the old German port of Memel? Catalytic effect. The catalysts are like a cold drink on a hot summer's day. He put all the variables he had changed in 3 weeks back to normal conditions. He turned on all the aerial cooler fin fans. The CO2 dropped below 0.2% in the hydrogen product. The lesson is, if raising reaction temperature in a reactor promoting an exothermic reaction makes the reaction proceed further, the reactor is limited by kinetics and not equilibrium. The term exothermic means that heat is liberated in the reaction. How can one tell if the absorption of CO2 in the catacarb solution is exothermic, gives off heat, rather than endothermic, absorbs heat? As shown in the picture. Note that both the hydrogen gas and the catacarb liquid are being heated in the absorber. They are being heated by the heat of reaction between the CO2 and the potassium salt in the catacarb solution. Zero-order reactions. Not all reactions are exothermic. Thermal cracking is an endothermic reaction. Heat is absorbed. Good thing, too. If thermal cracking of crude oil was exothermic, all the Earth's crude would by now have turned to coal and natural gas. Delayed cokers, visbreakers, and fluid catalytic cracking units are processes that are primarily endothermic in nature. A delayed coker operates with a zero-order reaction. This means the rate of reaction depends on time in the coke drum and the temperature in the coke drum. The composition of the products of reaction has no effect. On the other hand, hydrocracking is exothermic. The consumption of hydrogen liberates heat in the hydrocracking reaction. Runaway reaction. In 1968, a 3,000 psi G vessel exploded. This unhappy event occurred at the ESSO refinery in Bayway, New Jersey. The cause was a runaway reaction. Tar was being hydrocracked in an emulated bed of catalyst. The reactor got hotter, more hydrogen was consumed, and more exothermic heat of reaction was generated, which increased the rate of hydrogen consumption, which released more exothermic heat of reaction. I suppose if hydrogen feed had been stopped sooner, the runaway reaction could have been controlled. But it wasn't, and the reactor blew apart. An engineer had a similar, but less dramatic experience on a liquid-filled reactor, converting propylene to viscous polypropylene, a gasoline additive. The catalyst was aluminum chloride added continuously with a small pump. The pump malfunctioned. During its outage, we failed to stop feed to the reactor. The propylene content of the reactor increased. Finally, they restored the catalyst flow, but the liquid-filled reactor became very warm, very fast. Fortunately, an alert operator stopped the propylene feed to the reactor in time. Naphtha reforming. This is an endothermic reaction in a hydrogen environment taking place in the vapor phase. The catalyst is the size of grains of rice and contains very costly platinum, which sells for twice the price of gold. The objective is to produce aromatics benzene, toluene, or xylene. Benzene and xylene are the basic building blocks of the chemical industry. Steam hydrocarbon reforming. This is also an endothermic process. The reaction takes place inside catalyst-filled furnace tubes. Heat is supplied to the tubes by furnace firing. Almost any hydrocarbon can be used: natural gas, propane, butane. The objective is to make hydrogen. Most of the world's hydrogen is produced in this way. Half the hydrogen comes from steam and the other half from hydrocarbons. All of the carbon in the feed is converted to CO2 and vented. How hydrogen-powered cars will help global warming, I do not grasp. Alkylation. This is a very exothermic reaction. Isobutane and light olefins react to form isooctane, a gasoline blending component with a 100 octane. That's where the word octane comes from. Reaction takes place at 50 degrees Fahrenheit, in a liquid phase of either H2SO4 or HF acid. Polymerization. This is an old process using a solid bed of phosphoric acid. Reaction takes place in the vapor phase. Feed is normally propylene. Products are hexane and nonane. Polymerization is a very exothermic process. There is another sort of polymerization process used to produce viscous polypropylene. The reactor is a refrigerated kettle evaporator where the reaction takes place in the liquid phase. The catalyst was isopropyl chloride. The polypropylene product was used by Texaco in the 1960s as an engine top cylinder lubricant, added to gasoline 1 cc per gallon. The polypropylene is made at refinery. Sweetening. This is a slightly exothermic process. Mercaptans are converted to disulfides by adding air. The catalyst is a blue powder, Marex, which impregnates a bed of charcoal saturated with caustic. Converting mercaptans to disulfides reduces the bad smell of gasoline and jet fuel. The process takes place at about 100 degrees Fahrenheit. Sulfur content of the product is not changed. Hydrogenation motor oil is hydrotreated at 3000 psig and 450 to 650 degrees Fahrenheit to remove all aromatic compounds by contact with hydrogen. The resulting white oil is used for baby oil, mineral oil, and ladies' cosmetics. The white oil costs $5 per gallon to make and is sold for $30 an ounce in face creams. Fluid catalytic. Cracking reaction takes place at 1000 degrees Fahrenheit and low pressure in a riser pipe. The catalyst looks like white sand, but is actually made of zeolites. The catalyst picks up coke from the endothermic cracking reaction. The coke is burned off of the circulating catalyst with air. The catalyst gets hot, 1200 degrees Fahrenheit, and this supplies the endothermic heat of reaction. Half the gasoline sold in the United States is produced in this way. The original catalyst for this process was actually beach sand. Sulfuric acid. Sulfuric acid is produced by burning sulfur and H2S to SO2 with air. Then more air is added and reacted in a catalyst bed of vanadium pentoxide to produce SO3. The SO3 is mixed with water to make sulfuric acid. The reaction is exothermic and takes place in the vapor phase. Sulfuric acid is, by weight, one of the main chemicals produced in the world. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.